Welcome back to CS Connect series. This video we will be discussing about the set operations. So far we have been seeing examples in the previous video regarding a single set. We did not work with two or more sets at a time. This video we will be learning how to work with two or more sets together. Two or more sets can be combined in different ways. We will be seeing them in names of operation. But first we have to pick some example so that you can follow it for every operation. Let's take set A. This will be referring to the set of students who learn mathematics. Let's take set B. This refers to the set of students who learn computer science. The first operation that we are going to see in sets will be union of sets. What is union? We have to find the set of students who learn mathematics or computer science or both the subjects. We have to include set A elements. We have to include set B elements in this union of sets. We will actually learn every operation using Venn diagram. Based on Venn diagram, I'll tell you how it will be represented through notation. So let's take the universal set. And we have two sets A and B. When we say union of sets, set A is considered completely as well as set B is considered completely. So that is what you see as the shaded region here. The union of sets means selecting the elements from both the sets together. The union of two sets A and B is the set of all elements which belong to A or to B or to both. Here we have the common elements for A and B. Even this part is taken for union purpose. How do we represent them? We represent using this particular notation, A union B. So how will you describe this? We describe that there is an element. This element belongs to A or it can belong to B. And in other case, it can belong to both A and B also. So somehow it is in A or in B. That is what we denote by X belongs to A or X belongs to B. An element X belongs to the union A union B if X belongs to A or X belongs to B. Let's take A is equal to 1, 2, 3 and let's have B is equal to 4, 5, 6. The union will be 1, 2, 3, 4, 5, 6. So if I say A has 1, 2, 3, 4 as elements, the A union B will remain same. The next operation that we are going to see is intersection of sets. Now what is intersection? We have to get the set of students who learn mathematics and computer science. So it is not about the students who learn only mathematics. It is not about the students who learn only computer science. It's about the students who learn mathematics as well as computer science at the same time. So we will take the Venn diagram here. So this is where A and B meet together. So students whoever learn mathematics as well as computer science will be placed under this region. The intersection of two sets A and B is the set of elements which belong to both A and B. So if there is going to be 1, 2, 3, 4 as we took in the last time and B has 4, 5, 6. Now the intersection will be only the element 4 because A and B are going to have only 4 as the common element. X belongs to A and X belongs to B. It means it is available in both the sets. Every element X in A intersection B belongs to both A and B. So here we know 4 is belonging to both A and B sets. That's why we are picking up 4 as the answer. Now we will learn about disjoint sets. Since we saw about intersection, this disjoint sets has a point regarding intersection. What are disjoint sets? A and B are said to be disjoint or non-intersecting if they have no elements in common. Two sets are called disjoint if their intersection is the empty set. It means there are no elements there. So let's take the diagrammatic representation. Let's take an example. A is equal to 1, 2, 3 and set B is equal to 4, 5, 6. Do we have any intersection point here? No. A intersection B is actually empty. So this is what they mean by disjoint sets. Now we will see about disjoint union of A and B. Union means we know the elements of A and B should be taken together. So A union B will give 1, 2, 3, 4, 5, 6. Do you have any elements in A intersection B? No. So we can mark it as empty set notation. So A union B means both can be taken together, but at the same time we make sure that the intersection part is empty set. That is what they have represented using this disjoint union of A and B. So when we say disjoint sets, you can combine them under union, but you cannot find any intersection point between them. When they say intersection part is empty, we can tell them that they are disjoint sets. Next we will get into partitions. This is nothing but the set A. This set A is divided into 5 subdivisions. So this is actually called as partitions. Previously we saw the topic disjoint set. It means there are two sets, namely A and B, and they don't have any elements in common between them. That's why they are called disjoint. Here in this partition we are going to apply this disjoint property. A partition of set S is a subdivision of S into non-overlapping, non-empty subsets. What is non-overlapping? It means there is no intersecting element. There will be no common elements between these subsets, we can say. So they say non-empty subsets. It means every subset should have at least one element. What are the subsets that you can find in this diagram? A1, A2, A3, A4 and A5. A partition of S is a collection AI of non-empty subsets of S such that each A in S belongs to one of the set AI or one of the partition AI, we can say. Here this A is nothing but the element. So if there is going to be an element A, it will be present in one of the partition and not more than that. The sets of AI are mutually disjoint. So let's take for an example a set of elements ranging from 1 to 9. The partition 1 can have elements 1, 2, 3. Then the second partition can have 4, 5, 6. And the third partition can have 7, 8, 9. What can you understand from this is they are mutually disjoint. It means you don't have any intersecting elements here between any two subsets of this particular set S. You don't find any common element. That's why they are called mutually disjoint. Why do they mention the term mutually is between any two sets it is applicable. It can be between A1 and A2, it can be between A1 and A4, it can be between A2 and A5, A3 and A1, anything. And what do they say here? AJ is not equal to AK. So at a time you are comparing two subsets and they say they are not equal. It means they don't contain the same elements as well as same number of elements. First set may have only 1 and 2, while the second subset can have 4, 5, 6, 7 and the third subset can have 3, 8, 9. It can be partitioned into any way. And they say the intersection between these two sets will be empty set. It means this particular set will be subdivided in such a way that the elements will sit exactly in one partition, and if that element sits in one partition, it will not be available in another partition. That's why they say the intersection part is empty set. The subsets in the partition are called cells. So here if you take this diagram, you can say it's a cell here. Now let's go to an example. Consider the following collections of subsets. So they have given the S set here 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's take the first collection. The first subset has 1, 3, 5. The second subset has 2 and 6. The third subset has 4, 8, 9. They are asking whether this is a partition or not. This is not a partition. Why it is not a partition? Partition means if you have 9 elements, all the 9 elements should be subdivided into some partition. You should not miss any element. That's why they say each element belongs to one of the partition that is present or one of the subset that is present. You should not miss any element. But here we have 1, 2, 3, 4, 5, 6, 7 is not there, 8 and 9 are there again. Element 7 does not belong to any subset, so we cannot consider this to be a partition. Now let's take the second one. We have 1, 3, 5 as one subset, 2, 4, 6, 8 as other subset, 5, 7, 9 as other subset. Is this a partition? Let's check. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So one condition is fine. Each A belongs to one partition. What is the second condition? There should be no intersection point here. If we take 1, 3, 5 and 2, 4, 6, 8, there is no intersecting point, it's fine. What about the second and the third subset? We have 2, 4, 6, 8, 5, 7, 9. Here also there is no issue. Let's take the first one and the third one. We have 5 as the intersecting element, which is actually violating the second rule. This is not a partition of S because these two subsets are not disjoint. It means they do have one intersection element which is making them as non-disjoint sets. Now let's take the final example. We have 1, 3, 5 here, 2, 4, 6, 8 as second one and 7, 9 as the third subset. 1, 2, 3, 4, 5, 6, 7, 8, 9. All the elements are present. What about the intersection part? First one and second one don't have any intersection. Second one and third one don't have any intersection. And first and third one don't have any intersection. From this we can conclude that it is a partition of set S. Why did I stop with intersection and take you to disjoint and partition is disjoint concept and partition concept are stating where the intersection part should be empty. The extension of that disjoint concept is what we call them as partition, where you are dividing the sets, making them mutually disjoint. Now we are back to the next operation. Complement of set. Here only one set will be involved for this operation. So union is between two sets. Intersection is also between two sets. But complement belongs to one set. We are just restricting to set of students who do not learn mathematics. So let's take the universe here and this is A. If it is A, these people learn mathematics. When it is A complement, we say do not learn mathematics. That's why we have shaded this part outside A. If I say who do not learn computer science, you have B set who learn computer science. Then do not learn will be anything other than B. So this is B complement. The complement of a set A is a set of elements which belong to U but which do not belong to A. So whatever element is present in A, that will not be taken for complement purpose. A complement can be represented as A bar or A to the power of C, stating that it's a complement. X belongs to U but X does not belong to A. This is the main thing that you need for complement. Now let's consider an example. We did not get into the concept of universal set, but let me take a set S. So let me take some 6 elements. Consider this to be the universal set as of now. We have a set A which holds the element 1, 2, 3, 4. Now what is A complement? Whatever is not present in A, that will be included in A complement. So what is not present in A? From the set S we can infer that 5 and 6 are not present. So the A's complement will be the set with elements 5 and 6. Whenever you have a set A and you have A's complement, when you take union of these two sets, you automatically get the universal set. It means the set S as per this example. Just for the sake of explaining you, I have just picked up a set of 6 elements from which we calculate A complement based on the given set A. Next we are moving to difference of sets. We want to pick the set of students who learn computer science alone but not mathematics. So we will take A and B here. This is Max, this is CS, and this is Max and CS together. When I say I want only people who learn CS but not Max, this should be taken totally out. So only this shaded region will be covering the students who learn computer science but not mathematics. If you take B completely, B has people who learn CS. It is not worried whether they learn Max or not. There are 2 categories. Here, whoever learns Max will fall under the intersection part in this diagram. So we are removing this part and keeping only this region where only CS students are present. The intersection part is taken out. So let's take A is equal to 1, 2, 3, B is equal to 3, 4, 5. So the difference operation will give 4 and 5 alone. We are not going to include 3. So this is, we can equate it to max and this to be CS. So when I say only CS, only these people are in CS part. This particular 3 is present even in A, which states that this person learns both maths and computer science. I don't want mathematics to be selected here. I want only computer science to be selected. So in that way, we are shading only the B region, which excludes the intersection of A and B. The difference of B and A. So we are selecting computer science and not maths means B comes first and A comes next. It is the set containing those elements that are in B but not in A. So when I say it is B minus A, I have to check 3, 4, 5 minus 1, 2, 3. So minus is the symbol we usually use for difference. We have to choose elements in B but not in A. 3 is in A, so we don't choose 3. But these two are not in A, so we choose 4 and 5 as the answer. It is denoted by B backslash A or B minus A. Generally we use this notation. X does not belong to A and X belongs to B. Usually they will tell you the difference using A minus B concept. So when you take A minus B, what happens? This is A, this is B. If you take people who learn mathematics and not CS, that will be A minus B. So in that case, only A part will be shaded. Only max part will be shaded. This is maths and computer science and this is computer science. We are ruling out both the region. We are picking only the region where maths people are totally present. So since we are into computer science, I just made it as B minus A. The difference of B minus A is also called the complement of A with respect to B. Let's take this to be A. What is A's complement? Except A, everything will be A's complement. This complement of A is with respect to B means only the B's part is taken, not the universe part. So once again let me say, if I take A complement will be anything in the universe. I am going to consider only this part. For difference, it means it is A's complement but with respect to B. So if it is A minus B, we can say it is the complement of B with respect to A. You have to know in what angle it is connecting to complement because questions may even arise from these statements. After difference, we have something called symmetric difference. Set of students who learn mathematics or computer science but not both. From this what you can understand is intersection part elements should not be there in symmetric difference. So let's take the diagram. Except the intersection part, you can shade everything. So this is like union minus intersection. A union can be there, but you have to exclude A intersection B. That is what we can tell as symmetric difference. They learn maths, this is maths. They learn CS, this is CS. So maths or CS is fine. What about not both? Maths and CS is what this intersection states. We are not including them. The symmetric difference of A and B consists of those elements which belong to A or B but not to both. So it can either be in A or in B but not in both. Let's take A is equal to 1, 2, 3 and B is equal to 3, 4, 5. 1 is there in A, so we are selecting. 2 is there in A, we are selecting. Can we select 3? No, because it is available in A and B. It should not be in both. So we are excluding 3. 4 is available only in B. 5 is only available in B. This will be the symmetric difference of A and B. The denotion is using this symbol and we denote it using A union B minus A intersection B as I mentioned here. There is also another way to express this. A minus B union B minus A. So using the difference operation they have mentioned this. Let's take the difference operation. For A minus B we are shading only this part. For B minus A, we will be shading only the B part. Now you have to find A minus B union B minus A. How will you do that? So let's take A and B. Only the A's part this side and only the B's part this side. Is this equating here? Yes. That is what they say. A minus B union B minus A. This will give you the symmetric difference of two sets. So when you find what is the intersection of two sets, definitely the complement of intersection will be symmetric difference. Let's take for an example. What is A intersection B here? It is 3. What is A intersection B the whole complement? We can state it as 1, 2, 4, 5. With this we are completing the operations of sets. We have another concept here. Since sets are unordered, it means you don't have any specific order stating this is the first element or this is the last element. We have a different structure that is needed to represent ordered collection. The ordered n tuple. When you represent a set of elements using this brackets, it will be called as tuple. The ordered n tuple A1, A2, An is the ordered collection. Here we say A1 is the first element, A2 is the second element and An is the nth element. When you take the sets as 1, 2, 3, this can also be written as 2, 3, 1, then 3, 1, 2. In any way you can represent them. This is what the set notation means. But when you mean a tuple 1, 2, 3, the order stays the same. Because here 1 is the first element, 2 is the second element and 3 is the third element. Two ordered n tuples are equal if and only if each corresponding pair of their elements is equal. Let us see in generalized form. You have one tuple with A1, A2 till An element. You have another tuple from B1, B2 to Bn element. We can say that they are equal if and only if each corresponding pair is equal. What is a corresponding pair? A1 and B1 are corresponding pairs. A2, B2 are corresponding pairs. Similarly, A and Bn are corresponding pairs. If and only if Ai equal to Bi. For I is equal to 1, 2, 3, etc. up to n. When I say it is A10, then it will be equal to B10. N tuples they have given, which states that the number of elements also should be same in both the tuples. Only then you can equate it using the suffix here. Ordered two tuples are called ordered pairs. If we say A, B and C, D are equal, if and only if A equal to C and B equal to D. So instead of this generalized form, they are just restricting it to two element here. Next we are seeing about Cartesian product of sets. The Cartesian product of A and B is the set of all ordered pairs A, B, where A belongs to the set A and B belongs to the set B. A cross B is equal to A, B. A belongs to A and B belongs to B. This is what they have given in description format. Let's take for an example. How do you find the Cartesian product of A is equal to 1, 2 and B is equal to A, B, C. Now let's take 1, 2 is present here. And we have A, B, C. Ordered pair means you have to pick the first element from A. Let's take 1. What are the elements in B? We have A, B, C. For every element in B, you should have the first element of A. So this becomes 1, A, 1, B, 1, C. Now what about the second one? You have to place it here. Again you go for A, B and C. So this should have 2, A, 2, B and 2, C. So this is how you will be finding the Cartesian product. Actually inside the Cartesian product what are we using? We are using the ordered pairs A, B. A cross B is equal to 1, A, 1, B, 1, C, then 2, A, 2, B and 2, C. Enclose them using the set symbol. That will tell you it is a Cartesian product of A and B. Cartesian products A cross B and B cross A are not equal. Why are they not equal? Now just consider B is equal to A B, C, A is equal to 1, 2. For every element of B, we will have every element of A. So let's take A, it is 1, then we have 2. So again A. Then for B, we have 1, 2. Then for C, we have 1, 2. What are the ordered pairs now? A, 1, A, 2. B, 1, B, 2. C, 1, C, 2. Now this is B cross A and this is A cross B. Are they equal? They are not. That is what they say, they are not equal. So either A should be empty or B should be empty. So that the Cartesian product will also be empty. Either that should be the case or A equal to B should be the case. It means when you have A is equal to 1, 2 and B is also equal to 1, 2, A cross B will be equal to B cross A. This is possible because we have the same elements in both the sets. Now let's see a generalized statement. The Cartesian products of the sets A1, A2 till AN is the set of ordered n tuples A1, A2, till AN where AI belongs to set AI for I is equal to 1 to n. They say A1 belongs to A1, A2 belongs to A2, A3 belongs to A3. This is how they have meant by AI belongs to AI. This statement is mathematically expressed in this way. Now we will see a concept called fundamental products. Consider n distinct sets. All are different sets A1, A2 and AN. A fundamental product of the sets is a set of the form A1 intersection A2 intersection till AN where AI is equal to A or AI is equal to A complement. I am not getting into A1, A2 and A3 now. Let me tell you with an example. Let's take three sets A, B and C. The intersection of all these three sets can be taken as A intersection B intersection C. Forget about B and C. What is A complement? It is available in this universe. Forget about A and C. What is B complement? It is except B, you have everything. Forget about A and B. What is C's complement? We have it here. So I am just marking it in every corner to give you clarity. What do you find in common here? A complement contains some parts of B and some parts of C and the universe part. B complement contains some parts of A, some parts of C and the universe part. C complement contains some part of A, some part of B and the universe part. What is common between all the three? The universe part is common here. Except for A, B and C themselves, this universe part is the intersection point of all the three. So if we mark this particular part as the intersection point, then the intersection of their respective complements will be the universal part. So this is what they say. Everything can be expressed in the form of intersection where the set can be taken as the set itself like A intersection B intersection C, or the set can be treated with the complement of the set. So here we are expressing it in the form of A complement, B complement, C complement. This is what they have explained in this statement. How many regions are there? We have 1, we have 2, we have 3, we have 4, we have 5, we have 6, we have 7 and we have 8. The outside part is also a region. All these 8 regions can be expressed using intersection point. But how is this intersection applied? It should either be applied to set A, B, C or to A complement, B complement, C complement. So using only these 6 variables, we will be able to use the intersection operation to represent all the 8 regions. Now if I start telling you the other regions, you can understand this in a better way. What is this part? We know this is A, but what is also present in the A? When I took B's complement, A is covered. So B's complement is a part of this particular region. When I took C's complement, this A is covered. So inside A, I have C's complement also. So when I say it is A intersection B complement intersection C complement, it is this region of A which excludes A intersection B, A intersection C and A intersection B intersection C. all the intersection parts are excluded and only the A part is considered here. If you take this shape, this is A intersection B complement intersection C complement. Similarly, the next shaded region is, we have B here. A's complement is available in B, C's complement is available in B. So this region is A's complement intersection B intersection C's complement. What about this region now? We have C as it is. We have A's complement in C. We have B's complement in C. That's why we are including A's complement intersection B's complement intersection C. If you take this part, this is A intersection B with respect to AB. But when you have C, this is actually A intersection B intersection C, and this is completely C. So if you take in this aspect, anything apart from C will be C complement. So this part is C complement. That's why A intersection B intersection C complement is mentioned here. We know this is A intersection B intersection C. So anything above this region will be C complement because you are getting out of the boundary of C here. So that's why it is C complement here. Similarly, we have B intersection C here and A intersection C here. If you take this region, A intersection C is fine. But what border is this? This is B's border. So this will be B complement. What about this region? We know A border is finishing by here. So we will have A complement with intersection. A complement intersection B intersection C. I have cleared the screen for better clarity. Now the diagram will be very clear for you. There are m is equal to 2 power n such fundamental products. What is this n? The number of sets. So the number of sets is equal to 3 here because we have set A, B and C. And what is the number of fundamental products? M is equal to 2 power n. So 2 power 3, which is equal to 8. Did we get 8 regions here? I have marked all the 8 regions in different colors to show you which region has which boundary. And this universe part is alone kept in white to completely differentiate the Venn diagram from it. Any two such fundamental products are disjoint. Here you cannot find any intersection point between these two products. 8 products correspond to 8 disjoint regions. The universal set U is the union of all the fundamental products. Here fundamental product is, we are expressing each of the region in this particular format using the intersection format, as well as we take either A or A complement as a whole. Now we'll get on to the practice problems. Let U is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9 be the universal set. A is equal to 1, 2, 5, 6, B is equal to 2, 5, 7, C is equal to 1, 3, 5, 7, 9. Find A union B, B intersection C, A symmetric difference B, A complement difference C complement. So let's take A union B. So what is A? We have 1, 2, 5, 6 and B 2, 5, 7. So A union B will be 1, 2, 5, 6 from A. 2 and 5 are already present. So we will include only 7 in union set. So you have to have distinct elements. You should not repeat them. This will be the union of A and B. What about B intersection C? B is actually 2, 5, 7 and C is 1, 3, 5, 7, 9. What are common here? 5, 7, 5, 7 is common. So B intersection C is equal to 5, 7. What about A symmetric difference B? So you have two ways to do it. One is A union B difference A intersection B, or you can have A minus B union B minus A. I am just carrying on with this part. We know A union B we have already computed in the above part. What about A intersection B? What is common between A and B? We have 2 and 5 as common in A and B. So let it be 2 and 5. Now we have to find A union B minus A intersection B. Whichever is present in the union should not be present in the intersection. 1 is present only in the union. 2 is present in both, so we are not taking it. 5 is present in both, we are not taking it. 6 and 7 are present only in union. This will be the answer. Shall we cross check? What is A minus B? It has to be present in A but not in B. 1 is present in A, 6 is present in A but not in B. What is B minus A? 2, 5 are present in A, 7 is alone not present in A. Now A minus B union B minus A. What will you get? 1, 6, 7. Do we get the same answer? Yes. Now we have to find the difference between A's complement and C's complement. Let's find A's complement. What is actually A? 1, 2, 5, 6. A's complement will be 1, 2 means we have 3, 4, 5, 6 is present, 7, 8, 9. What about C's complement? 1 is there, 2, 3 is there, 4, 5 is there, 6, 7 is there, 8, 9 is there. So this is A's complement and this is C's complement. What is A's complement difference C complement? It should be present in A but not in C. A it's okay, not in C. Now we will take 3. 3 is present in A but not in C. 4 is present in A and C, so we will not consider 4. 7 is present only in A and not in C. 8 is present in C as well as A. 9 is present only in A. So the difference between A's complement and C's complement will be 3, 7, 9. Next problem. Find the sets A and B if A difference B is equal to a particular set, B difference A is equal to a particular set, and A intersection B is given a particular set. They have given the result of the operations and they have asked to find what are the sets. Let's take the given values. A minus B is given as 1, 5, 7, 8. It means these elements are present in A but not in B. Regarding the set A, we can take 1, 5, 7, 8 are present. And we know B does not have any of these elements. What about B minus A? Elements are present in B but not in A. So definitely B has 2, 10 and they are not present in A. What about A intersection B? These elements are present in both A and B. It means A will have 3, 6, 9 and B will have 3, 6, 9. Now if you compute A minus B, you will get this answer. If you compute B minus A, you will get this answer. If you compute A intersection B, you will have this answer. Now we will just arrange it for readability purpose. 1, 3, 5, 6, 7, 8, 9. B is equal to 2, 3, 6, 9, 10. Next problem. Let A is equal to 0, 2, 4, 6, 8, 10. B is equal to 0, 1, 2, 3, 4, 5, 6. And C is equal to 4, 5, 6, 7, 8, 9, 10. We have to find two sets of operation. The first one and the second one using Venn diagrams. Let's take the first one. A minus B union A minus C union B minus C. Let's take the sets A, B and C. Let's find A minus B. What is A minus B? It should be in A but not in B. This part is A minus B. We know A is equal to 0, 2, 4, 6, 8, 10 and B is equal to 0, 1, 2, 3, 4, 5, 6. What is present in A but not in B? 0 is present, 2 is present, 4 is present, 6 is present. 8 and 10 are alone not present in B. So A minus B will give you 8, 10. Next we will move on to A minus C. It will not cross this border. So this is A minus C. Let's take the sets. A is equal to 0, 2, 4, 6, 8, 10 and C is equal to 4, 5, 6, 7, 8, 9, 10. So we have to find A minus C. 4 is there, 6 is there, 8 is there, 10 is there. A minus C is equal to 0, 2. What about B minus C? You have to stop with this. This is B minus C. Let's take B is equal to 0, 1, 2, 3, 4, 5, 6. C is equal to 4, 5, 6, 7, 8, 9, 10. 4, 5, 6 is present in C. So the answer will be 0, 1, 2, 3. This will be B minus C. We have to join them together using union operation. Union operation will join all these three places together. So this is A minus B union A minus C union B minus C. Now we have to pick up A minus B 8, 10 union A minus C 0, 2 union 0, 1, 2, 3 as B minus C. What will be the union? 0 will be there, 1 will be there, 2 will be there, 3 will be there, 8 will be there and 10 will be there. I have just arranged them in ascending order, that's all. You can keep it in any order. This will be the answer of A minus B union A minus C union B minus C. We have one more expression to be evaluated. So let's take the set again A, B, C. Let's start with finding B's complement. What is B's complement? Except B, everything else should be covered. What about the value of B's complement? We have 0, 1, 2, 3, 4, 5, 6. So what is not present? 7, 8, 9, 10 is not present. That will be B's complement. So they have not given the universal set, but whatever is present in A and C but not in B will be coming under B's complement. What about C's complement? What is not present in C? 0, 1, 2, 3 is not present in C. So this is C complement. We have found B's complement and C's complement. Now we have to find A intersection B's complement and A intersection C's complement. Let's take A intersection B complement. So A is given here and B's complement value is computed already. So this is A and intersection B complement is this part alone. So what is present in A and B complement together? We have 8 and 10 in common. So these two are common. A intersection B complement will have 8, 10. Now what about A intersection C complement? Whatever is shaded in C complement, there you are finding only intersection with A. What is common between A and C complement? We have 0, 2. So A intersection C complement will be 0, 2. Now we have to find union between these two results. The union of 8, 10 and 0, 2 will give 0, 2, 8, 10. Next question. Find all partitions of set A, B, C, D. So when you are dividing a set, there are many ways to do. Say for example, there are 4 elements A, B, C, D. These 4 can be partitioned as 4 elements together. That is one possibility. You can take partitions as 2 and divide them into one partition. You can take A, B, C as a single partition and D as a different partition. There are possibilities of creating partition in many ways. We will partition as 1, 1, 1, element. It means we are considering only one element at a time. If that is going to be the case, we will have A, B, C, D inside the partition. This is one partition. When you have 1, 1, 2 elements, it means 2 elements can be taken individually. Other 2 elements have to be taken inside a set. If that is the case, we will have A, B, C, D. Then we have A, C, B and D as a set. Then A, D, B and C as a set. This is with respect to A. So from A, we are first pairing CD, then we are pairing BC, then we are pairing B and D. So 3 pairs can be found. So this is 2, this is 3 and this is 4. For B, what you can do? For B, you can pair A and C, A and D and C and D. 3 possibilities are there. So B, C, AD is a pair and B, D, AC is a pair. Why are we not including C and D? Because it is already done here. Whether it is B, A, C, D or A, B, C, D, there is no difference. So we are not duplicating this partition. So we are stopping with only 2 partitions. So this is 5 and this is 6. What about C? C will have 3 cases. AB pair, BC pair and CD pair. Already BC pair is done in A, CD pair is done in B. So the only left out pair is AB. So we can take it as C, D, A, B. This will be the 7th partition. Now we will partition it as 1, 3 elements. It means one element will be taken individually, the other 3 will be put in pair. So for A, what is the only option? We have BCD. For B, we have ACD. For C, we have ABD. For D we have ABC. So 4 partitions will be available here. So A comma BCD, B comma ACD, C comma ABD, D comma ABC. This will be 8, 9, 10, 11. What about 2 comma 2 pairs? If you are going to consider AB as a pair, then CD becomes a pair. If you consider AC as a pair, then B and D becomes a pair. If you consider A and D as a pair, then B and C becomes a pair. So this is 12, 13 and 14. So this 1, 1, 2, 1, 2, 1, 2, 1, 1 all are going to be same. Similarly 1, 3 and 3, 1 is also going to be same. What about all the 4 elements together as a set? This is the complete set taken as a single partition. This is partition number 15. There are totally 15 partitions that can be done, and all the 15 partitions are different. Next problem. Let A is equal to ABC, B is equal to XY, C is equal to 0, 1. Find the Cartesian product. When you find the symbol, you should know it is Cartesian product. A cross B cross C, C cross A cross B. So let's take in the form of a table. So first we have to start with A, B and C. C will have 0, 1 for the first value of B. So it is X. C will have 0, 1 for the second value of B. So it is Y. So X0, X1, Y0, Y1. This combination is for the first element as of now. So we will have A everywhere. Now the same set of combination X0, X1, Y0, Y1 will be taken for B. You have to maintain the order. A element should come first, B element should come next, C element should come next. This is A cross B cross C. What about C? The same set of pairs will be repeated. X0, X1, Y0, Y1. How will you write the Cartesian product? A cross B cross C is equal to, just have it in tuple form. A comma X comma 0, A comma X comma 1, A comma Y comma 0. A comma Y comma 1. This is how you will be writing. We will write it for B, B comma Y comma 0, B comma Y comma 1. Then we have C, Y 0. Then we have C, Y 1. So this is A cross B cross C. So we have to present in this format. That is what we have done here. What about C cross A cross B? So we have to start with C, then A, then B. So we will start with B value first. We have X and Y. Let's consider only A cross B here. So this is X comma Y and this is A comma B comma C. How will you represent? You will have A with X comma Y, then you have B with X comma Y, then you will have C with X comma Y. This is how we will be doing. All these stand for the first value of C, which is 0. So if you have another set in front, then it will be available for the first value. So it will be for 0. The same set of pair will repeat for 1. AX, AY, BX, BY, CX, CY. Now how will you write C cross A cross B? This is equal to 0 comma A comma X, 0 comma A comma Y, 0 comma B comma X, 0 comma B comma Y, 0 comma C comma X, then we have 0 comma C comma Y. This is one set, and the second set is 1 comma A comma X, 1 comma A comma Y, 1 comma B comma X, 1 comma B comma Y, then we have 1 comma C comma X, 1 comma C comma Y. A has 3 elements, B has 2 elements and C has 2 elements. So this is 3, 2 and 2. The cardinality they are saying. A into B into C will give you 3 into 2 into 2. Altogether 12 ordered pairs will be present. So 12 pairs are there. What about C cross A cross B? 2 into 3 into 2 will give you 12 ordered pairs. Here also you have 12 ordered pairs. This is how we will be working with Cartesian product. You have to maintain the order of the sets. Next question. If A minus B is equal to A intersection B complement, This defines the difference operation in terms of operations of intersection and complement. This is what I have been telling you while I was explaining. There are other ways to represent difference and symmetric differences. One such expression is given here. A difference B can be represented in the form of intersection and complement. Now they have asked us to find a formula that defines the union A union B in terms of operations of intersection and complement. In order to understand this particular expression, we are using Venn diagram. Let's take A minus B. What about B complement? Except B, the whole set is taken. A intersection B complement will be only the A part, that is in intersection part. Do you find A minus B and A intersection B complement to be same? Yes, it is same. Now just think in terms of A union B, the complete part should be shaded. Now we have to use intersection and complement. We can find A complement. A complement will take every part of B. Then we will find B's complement. That will also take A and the universe side. So with that we will try to compute A union B. So this is A union B. This is the result that we have to get, but using intersection and complement. Let's start with A complement. So except A, all the regions are shaded. Let's go to B complement. B complement will have all the regions shaded except for B. Now we will find the intersection point of A complement and B complement. So A complement intersection B complement will have the complete universal part to be shaded. In A's complement, A is not shaded. In B's complement, B is not shaded. So when you take intersection, these two parts will not have the shade. Now what do you need for A union B? You need only the A and B part. But except that, everything is shaded here. What operation if you do on this particular diagram will reverse it? If you do a complement operation, it will reverse the shaded region. A complement intersection B's complement is taken as a whole for the complement operation. Now do you find both these diagrams to be same? Yes. From this we can conclude A union B is equal to A complement intersection B complement the whole complement. A union B is expressed in terms of intersection and complement. So this will be the answer to the question. The final question, the successor of the set A is the set A union. The set A is inside the set again. So find the successor of the following sets they have given. A union, the set of A is adjoin the set itself to the list of its elements. Say for example, if you take 1, 2, 3, along with 1, 2, 3, you have to include the complete set of 1, 2, 3 as an element. Let's see how to do that. So this is 1, 2, 3, the individual elements, and the whole set is inserted as a new element. This is what we call as successor of the set. Now what about null? We have to take null and pass it as an element to the set. So what is engenderally null? Null means it's an empty set. If you insert null to an empty set, what will you get? You will get set with an empty set. Now what about set with null set already? So you have like this, and you have the set here. You have to insert it inside. How will you insert it? First you have to insert the element null, and then you have to insert the set itself. You have an element inside, so place the element and then place the set itself as another element. Now what about this one? You have two elements here, so place these two elements and then this set as another element. Let's take A comma B. How do you find the successor? Just take A comma B comma the complete set A comma B. So understand, when they ask for successor, along with the element you are going to insert one more element, and that element will be the set itself. So with this we are completing set operations video. I'll meet you in the next video. Thank you viewers.